let's start off with the line geometry, because I think that's the one that most people already have an intuitive feel for. So let's start off with that. So the line geometry, it would look like, well, line of current. I guess the way I wrote it, I probably should do it horizontal. So let's say you have current that comes in from one end, goes in a straight line, and then leaves off at the other end, and it just continues on. You have to imagine it as being infinitely long. So what do magnetic field around this current carrying wire look like? Yeah, you can use the shortcut right-hand rule, where your thumb points in the direction of the straight wire, and the direction your fingers curl around is the direction that the magnetic fields go in. So if you have an intuitive feel for magnetic field, that this is the direction. So looking at the side view, it would be coming out of the board here, going into the board here. Or if you're drawing it as a perspective view, then it sort of comes out here, loops around this way, goes in here, and then loops and goes behind the wire. So it's a loop that goes around the wire. Okay? Yeah. So if you have that vision of the magnetic field, so that's the direction of the magnetic field. So what kind of symmetry would you call this? Like, so think back to when we were dealing with the Gauss's law. We talked about symmetry and how you define symmetry in a precise way. You define a symmetry operation. Some kind of transformation you can do to this and not have anything change really. So what kind of linear transformation can you do to this and not have anything change? There's a rotation, any kind of rotation, or only a specific kind of rotation? Rotation along an axis or around an axis that's going along the wire, right? If you're rotating around this axis, then no matter how many degrees you're rotating, nothing will change. Good? Any other symmetry? Some translational? I think you meant a translational. Transitional is not a yeah. So what kind of translational symmetry? Because it's not true that every translation will be a symmetry operation. So what direction? Yeah, along the wire again. So this is actually a symmetry that this exhibits only because it's infinitely long. If it's a finite rod like this, you translate it, it's not symmetric, you change it to something. But if this is an infinitely long rod, then when you move it a little bit, nothing really changes because it's infinitely long. Infinity away is still infinity away when it moves closer to you by a meter. So that's the two kinds of symmetry you see with this geometry. And you can kind of see that symmetry in the magnetic field too, because the magnetic field is going around this wire. So when you rotate it, and imagine magnetic field, a point rotating with it, nothing's really changed. If the shape of the magnetic field looks like a circle around this wire, when you rotate them together, nothing's really changed. So that symmetry that you're noticing here also is reflected on the magnetic field. And the second symmetry, the way it would be reflected is when you look at the magnetic field at this location and look at the magnetic field at some other location, it would be the same field. Because, the other location would be this translated over here. And the translational symmetry means that magnetic field at these two locations are the same. Once again, this is something you have only with the infinitely long line. If you have something that's finite, you don't have that translational symmetry. You should still have the rotational symmetry, but not the translational one. So, okay, so everyone's okay with the line geometry. Let's look at the planar geometry, because this is the one that it's kind of fun. You haven't seen it before, so it'll take a while for us to figure out exactly what the magnetic field looks like. Let me draw it this way. I'm going to draw it the same way I drew it last time. So I'm going to imagine if this is a line of charge, imagine that this is moving into the plane or into the board. Or what I mean would be like, so this is my plane of whatever current carrying thing. And there's a wire, wire of current going in here, another wire right next to it, another wire right next to it, and so on. So when you draw the side view, this is what the plane would look like. And the current would look like it's going into the board. Let's first start by noticing some symmetry here. What kind of symmetry does this plane of current exhibit? Okay, translational symmetry. Translation in what direction? Like any translation within the plane, right? If you translate this plane to the right or left, then nothing changes. If you translate this plane forward or backward, nothing changes again. Good? So it has translational symmetry. Any other symmetry with this plane? Any other symmetry? Rotational symmetry? Not really. You take the plane and rotate, you have changed something. Okay, so when we figure out the direction of magnetic field for this plane, that's going to be consistent with this translational symmetry. So what do you think a magnetic field will look like? Takes a bit of thinking because it is unusual once again. Let me just draw a few that you already have intuition for. Like if I had just this wire, you have intuition for that, right? Use the right-hand rule. Thumb goes into the board, magnetic field wraps around this way. So you might say, okay, this produces a magnetic field that looks like this. Now, if you look at the magnetic field that looks like this, well, that doesn't have translational symmetry, right? Because you translate it and things are changing. So what you have to imagine is that each one of these wires are producing its own field. So using superposition principle, you have to imagine what the net magnetic field, let's say at this location, looks like due to all the wires around it. It's going to be a straight line, yeah. So straight right line in what direction? To the right, right? Because that's what you see here. All these magnetic fields due to different, they all seem to be pointing to the right in general. So if it's going to be straight line, it will be straight line this way, pointing to right. That'll be your magnetic field. So let me draw that. So that will be up there. All right. And I guess from the symmetry, one thing you can say is whatever the magnetic field is at this location, it'll be the same magnetic field way over here, same magnitude. Because you can imagine translating the whole thing and nothing would change. Now, does the symmetry tell you how the magnetic field at, let's say, point A compare with the magnetic field at point B? Does the symmetry that's in the current tell you how the magnetic fields at point A and B compare? Not really, right? Because if you translate up or down, that'll change your current distribution. So this is something we are going to need be able to figure out using Ampere's law. So we'll get to that as we are applying Ampere's law. But for the purpose of symmetry, this is what we can say. Magnetic field at point C and D are the same. Magnetic field here is the same magnetic field out here. I guess I'm using too many letters. What about the magnetic field below the plane? Yeah, straight line to the left. Yeah. So so this is what the magnetic fields over plane look like. It has an odd similarity to what the electric field due to a plane of charge looked like. As in, electric field due to a plane of charges was also straight line. Straight line going up and down, right? So with the magnetic field, it's the same kind of symmetry. So it's a straight line, but it's a straight line going the other way because once again, magnetism is complicated. Yeah. Okay, so these two, you can figure it out from your intuition. And I think actually you can figure out for solenoid and toroid as well. So let me draw them and we will talk about it. So what a solenoid would look like, let me draw it the same way I drew the line. I will draw it horizontally. So what it should be is that it's a series of rings. So series of so normally when we actually build a solenoid, I connect this wire so that I can have the same current, but like it doesn't actually have to be imagined that way. If you imagine just having a very closely spaced rings at an even density, then I get tired of drawing this. So what you have to imagine is, so I've drawn a section of solenoid here, but this is going to be a very long solenoid. It's just going to keep on going. So for the symmetry to be perfect, this has to be an infinitely long solenoid. Imagine having something like this that is infinitely long. So when we are dealing with a real physical solenoid, what we talk about here will be an approximation. But saying that this is infinitely long allows us to make the approximations we're going to make. So let's talk about the magnetic field directions. So I won't draw the full field lines because there's much we know. But I think we can at least figure out the direction. What do you think magnetic field direction will be? Along the very center of solenoid. Straight. Oh, wait, I didn't specify the current direction, right? Let's say current is coming out of the board here, going into the board here. To the right? So if you are looking at magnetic field along the center, then you have a sense from symmetry, okay, that should go in a straight line to the right. Yeah. Okay, let's go over toroid. So toroid is the hardest one to draw. So let me draw the perspective view for the solid body of the toroid. But that's not what we call toroid. What we call toroid is this, this is just a donut. That's all it is. At least I don't call this toroid, maybe some people do. What we call toroid is where you have a wire wound around this donut-looking thing. So so let me draw the donut-looking thing in a perspective view. So here's the hole. Here's the outer thing. And I'm going to actually make it the same way as this toroid that you have seen. I'm going to say there's what's the shape of its cross section? Is it a circle, square? It's a rectangle, right? So I'm going to say there's a rectangular cross section also. So when I draw the cross section here, this cross section will appear rectangular. And I'll just finish drawing here. All right. All right. So, oh wait, sorry, I messed up the color. I've been drawing wires with green, and with the toroid, sorry, I should have done this in black, because what I just drew is not the wire. Okay. This is something, so what I just drew here, it's something different from the current carrying part of the toroid. And the actual current carrying part of toroid is what I'm now going to draw in green. So the current carrying part of toroid is one that wraps around this way. So let me do it this way. Let's say the current is going from in to out here, and then down here, and then back this way, up, and then it keeps winding this way, and you have to imagine this going on around the whole thing. So out here, it would look like it's coming out of the board, down, and then going into the board, and then up, and it keeps winding around. Yeah, I don't want to draw the whole thing, which is why I sent this around so that you have a mental image of what it is. So with the current distribution described here, With the toroid, we are going to be actually more limited. We are not going to talk about the magnetic field outside the toroid at all. We are only going to talk about magnetic field inside the toroid. So, so on this plane, what do you think is, or on this cross section, what do you think the direction of magnetic field is? Sorry. So the direction I talk about. Okay. So I have this wire wound around the way I described there, and imagine cutting this toroid at this portion. So there's a plane that's cutting the toroid here, right? And I'm asking you for, okay, what is the magnetic field at the point on that plane, in that plane? Into the board or out of the, so you do have the sense that if my loop of current is going more or less inside, in the plane of the board, then you do have the sense that the direction of magnetic field will be either into or out of the board, right? It's out of the board, right? So if you, which shortcut right-hand rule would you use to figure this out? So you could do it along the wire, but that's not the shortest shortcut. There's the shorter shortcut, right-hand rule. The one I would use, the shortcut right-hand rule involving a loop. It's the same thing you did. I assumed it was the same thing that people did for solenoid, right? So the shortcut right-hand rule for loop is that you make your fingers curl in the direction of the current in the loop. Then your thumb points in the direction of the magnetic field inside the loop. Right? Because with the solenoid and toroid, your very basic constituent part is a loop. So for the intuitive sense of figuring out the direction of magnetic field, it loops around this way, so magnetic field must be coming out of the board. Okay, so magnetic field here is coming out of the board. Magnetic field here is going into the board. What about in between? What do you think magnetic field should look like? Like imagine you are taking this toroid and looking at it from above. What would the magnetic field line look like? Like circle, right? Circle going around the donut. Yeah, so that's going to be the magnetic field. And I guess that more or less completes that geometry. So magnetic field line, if I look at it from above, it's going to look like a circle going around the body of the toroid. And it matches the rotational symmetry. So the symmetry that, I think that's the only symmetry that toroid has. It has rotational symmetry in the sense that if you rotate it around the axis going through the center of the toroid, then nothing changes. And this particular geometry for the magnetic field will be consistent with that symmetry. When you rotate it a little bit, magnetic field doesn't change at all. Okay? So, so these are the four geometries where we can use Ampere's law to try to figure out the magnetic field. And the reason we couldn't start out with Ampere's law was that for you to have all this intuitive feel for the direction of magnetic field, you have to develop it using Biot-Savart's law. So